The work energy theorem, or principle, states that the amount of work done is equal to the amount of energy transferred to the body. So if we do an amount of work on a body equivalent to 50 joules, that means that we have transferred an amount equal to 50 joules of energy to the body. Now, work can be done by the application of a force through a distance, and there may be an angle between the two, cos alpha. And this leads to a transfer of mechanical energy to the body. Now, the mechanical energy can be one of three types, and we will look at each of these in turn. Now, the mechanical energy could be kinetic energy, it could be gravitational potential energy, and it could be elastic potential energy. The kinetic energy can be shown to equal 1/2 times the mass of the body times the speed of the body squared. The gravitational potential energy can be shown to be the mass times g times the change in height of the body. And the elastic potential energy can be shown to be 1/2 times the force applied times the displacement it causes. Or we will see this to also equal to 1/2 times the spring constant times the displacement squared. We shall now look at a situation whereby an amount of work transfers kinetic energy to a body. So let's say we have a little toy car and we apply a force on this car to the right. That force, if it's a net force, so consider a frictionless runway, will displace the body towards the right. If we apply the force through a particular distance, let's say d, eventually we'll give a type of energy to the body known as kinetic energy. So the work done on the body, which is equal to the force times the displacement times the cos of the angle between the force and the displacement, actually transfers to a kind of energy that we call kinetic energy. Now in this case, since the force itself is acting to the right and the displacement that it causes is also acting to the right, so in that case, considering the two, the angle alpha will be equal to 0, and therefore cos alpha will be the cos of 0, which is actually equal to 1. Now since the cos of alpha is equal to 1, the amount of work done is equal to simply the amount of force times the displacement, and that is what transfers kinetic energy to the body. Now, considering some mathematical manipulation with formulas that we already know in physics, we can substitute and say that the force is equal to the mass times the acceleration, but of course the acceleration is the velocity divided by the time, and that is multiplied by the displacement, which we can show that it's equal to 1/2 times v times t. It is clear immediately that the t's cancel out, and so we are left with 1/2 times the mass times the velocity again, so the velocity squared, and that is what is equal to the kinetic energy. So doing an amount of work on the body in this particular case actually translates to giving the body an amount of energy equal to 1/2 mv squared. So we can write this as Fd cos alpha equal to 1/2 mv squared. Let's look at a situation where doing work on a body transfers gravitational potential energy to the body. So let's consider a body of mass m, and let's consider lifting it up using a force F and displacing it a vertical height, let's say, let's call that height h, which is also the distance that the force moves. So the amount of work done is found by the force applied multiplied by the distance it's applied through, multiplied by the cos of the angle between the two, and that gives it a kind of energy due to position, which we call gravitational potential energy. Now the force that we will need to act to apply it, to move it upwards without giving it any other kind of energy, such as kinetic, in other words accelerated, it must be equal to the weight of the mass, and that is found by mg. And so applying a force equal to mg to move it through a distance h, which of course is the distance that it's moved through, and so that is a change in height. The cos of alpha here is equal to 1, since the force and the distance are in the same direction. And so we have very quickly come up with the formula, in which the work that was done, which is equal to the F times D times cos theta, or cos alpha, is equal to the gravitational potential energy gained, which we have quantified as mg times the change in height. It is perhaps clearer in this situation that doing work on the body gives it a kind of energy or position, which is called gravitational potential energy.